So hi everyone, my name is Sam Burns, and today I'm going to be talking to you about sensing supersuits, or how to develop a mechanochromic sensor based on fibers. So to start off, why am I talking about supersuits? I, like many of you, grew up loving superheroes, and particularly supersuits. And the reason I love them is that unlike traditional wearables like an Apple Watch or Fitbit, a supersuit isn't really a gadget. Instead, it's part of the user's identity. It's this perfect union between high technology and user-centered design that I really wanted to explore for the wearable space. So, if we're going to apply these supersuit design principles, where can we apply them? What if a back brace could tell you if the right amount of tension was being applied? Or your yoga pants could tell you when you had the right technique for a yoga move? Or a car seat could tell you whether you safely secured your child into the seat. All of these applications involved human movement and strain. So can we apply these supersuit design principles to strain-sensing smart textiles? And if we want to detect strain, there's a lot of different ways to do it, and a lot of different ways to communicate this data. My preferred method is color. Why? Color is very intuitive, and humans respond really well to color. You can see it's used a lot in marketing when we're talking about the future of clothing and the future of performance. And it has a lot of practical applications as well as a sensor. So it's a lot more cost-effective than digital sensors. You can design color-based sensors to be energetically passive. You get real-time sensing because you can see when the changes are happening. And if you can get color on the fiber level, you can get really high resolution. So the lab that I'm working with, the Shu Yang Research Group, has previous experience designing color-based sensors. So for example, here's a color-changing textile that that detects different chemicals in your sweat. So all of these factors really drove my design goal, which is, can we develop a mechanochromic fiber to tunably change color based on strain levels? And so the basic design of my fiber would have a sensing functional core and a protective, mechanically robust sheath. So on the modular fiber level, it would act as a sensor, and you could knit it into different textiles to get these supersuit-inspired sensing textiles. So the rest of my presentation, I'm going to walk you through my design process, which involves the material selection, the fabrication process, and ultimately the characterization of my technology. So to begin with, I mentioned generally we want functional core, protective sheath. What kind of materials do we really want to use for these? So to start off with the functional core, we're using a material called liquid crystal, which you may know through LCD displays. Liquid crystal are a type of very responsive material that modulates light in unique ways. So in an LCD display, it modulates light based on an electric field. But you can also have liquid crystal that's sensitive to an array of external stimuli, including temperature, pressure, magnetic fields, chemical sensing. The good thing about liquid crystal is that it's very commercially available, which is great for our very practically commercial-driven design approach. So what kind of liquid crystal are we using? We're using cholesteric liquid crystal, which modulates light in a very particular way. It self-assembles into a helix, and the geometry of the helix actually determines a certain wavelength that is reflected back. So you get color when that geometry is tuned for the visible wavelength. And you see this a lot in nature. So for example, you can see the green iridescence on a beetle's shell as an example. And there's actually been some previous work done on how liquid crystal behaves when it's encapsulated in a fiber. So the Lagerwall Research Group developed liquid crystal encapsulated fibers in a non-woven mat for temperature sensing, which was interesting, but not really super practical because they used very brittle and fragile fibers. But they did find a really interesting phenomenon, which was, when you have a liquid crystal fiber that's big enough, you get the properties of the bulk liquid crystal, but when you make them smaller, the color that you see is actually due to the confinement of the fiber and not due to the bulk properties. So because they were using brittle fibers, they weren't actually able to see what would happen if you dynamically change these boundary conditions. So this is what I really wanted to explore. Can we use this confinement effect to get a change in color based on strain? So in order to do that, we need to encapsulate this liquid crystal with a very mechanically robust sheath, which hasn't been done before. We're using a material called polyurethane, which you might be familiar with. It's a common component of spandex. It's very mechanically robust, very durable, and our research group has experience using this in other textile prototypes. So the viability of it for knitting applications and textile applications has already been proven for us. And how are we making these fibers? We're using a fabrication method called electrospinning. So it's a very highly tunable process, and you can change an array of these parameters in order to get whatever kind of size or morphology of fiber that you need. So now on to more of the experiments of this design process. We had to determine what the optimal composition of cholesteric liquid crystal was that we wanted to use. And we had a lot of options. These are an array of the liquid crystal we had in our lab, but not all of these are going to be viable for our application. So for one, because we want a discrete functional core and a protective sheath, we can't have the liquid crystal be too soluble in polyurethane. So as you can see, we had to do tests to see which liquid crystal phase separated from the polyurethane. In addition, after phase separation, you want to make sure that the bulk color of the liquid crystal is somewhere within the visible spectrum. So that eliminated a few compositions for us, so then we could begin our testing. So how do we get the right shape of fibers? Traditional solvents for polyurethane weren't really effective when trying to make these fibers. As you can see, you're getting really lumpy, bubbly fibers. This isn't really ideal for textile applications. So we had to do kind of a robust parameterization process in order to find what the best solvent was to use. As you can see, we kind of got this trade-off. When we use low boiling point solvents, we didn't get phase separation between the core and the sheath. On the other end, if we used high boiling point solvents and a high dielectric constant, we could get uniform fibers, but we couldn't get that phase separation. And to give you a little bit more context, we tried for every solvent, we tried different concentrations, different pump speeds, different applied voltages. So there was over 50 samples, nothing was working. When I was looking through the literature, I did find a solvent that would be a potential candidate. It had a high dielectric constant, low boiling point. No one in engineering had it. I wanted to make sure before I bought it, I knew that this could potentially work. So what I ended up doing is I actually Google searched for recent publications from Penn that actually listed this as a material over the past 2 years, emailed a few professors, and actually the Kozlowski group emailed me back and was like, yeah, come in and borrow a little bit of solvent. So thank you to them. We were able to test this solvent, and it actually was very successful in producing phase-separated and uniform fibers. So now that we have these fibers, how does this confinement effect affect the liquid crystal color? So as you can see, we have very uniform fibers. We achieved selective reflection, which has never been done before for a very flexible, commercially viable sheath. You can see that we're getting a few different colors here. So the next step will be to actually make that interface between the core and the sheath more uniform, which again will be tuning of parameters in order to achieve more uniform color for these fibers. Our next step will be then to characterize the sensitivity, which is a paired test between spectrometry and mechanical testing through an instron. And then we'll know the viability of our sensors and be able to actually continue our collaboration with Drexel to weave these into textiles. So in conclusion, we developed a proof of concept for a commercially viable mechanochromic sensor from polyurethane encapsulated liquid crystal. And we went through a rigorous optimization process in order to get there, and we're a step closer towards sensing smart textiles. So thank you so much, and I'll take any questions. Yeah, so they're doing a really cool project called Project Jacquard. And so what they're doing is weaving capacitive threads into fibers, or into denim jackets. So you can actually control your smartphone by touching your sleeve, which again is really compelling evidence that this is something that people want and people are really excited about. So I think it'd be really cool to think about how color could be another component to kind of complement what people are already thinking about with functional fabrics. Yes?
So you can see the material inside the sheet? Is that how that works? How does that work?
Yes. So yeah, so the liquid crystal will reflect the color. So when we're encapsulating the liquid crystal into the fiber, you want to make sure that the sheath is thin enough so you can actually see the selective reflection from the liquid crystal. And by going through the yarn production process, we're going to be working on increasing the alignment so you can get really strong intensity when you stack these fibers on top of each other.
How much of like a piece of fabric would need to be made up of this type of thread in order for it to be effective, give the kind of feedback that you're probably seeing?
Yeah, that's actually a really good question, and it's actually advantageous that you wouldn't need that many of these fibers in a yarn. What you would actually want is a mix between these sensing yarns and like black just polyurethane yarns, because that would actually enhance the contrast and you'd be able to see a really vibrant color. So again, I would need to actually test this to see what the critical amount is, but you'd want a balance, say like half and half, between control black polyurethane yarns and these like sensing functionalized yarns.
Is there a durability concern also? Like, do these, the color ones, are they just as strong as the rest of the material?
Yeah, that's an excellent point. So we're going to be doing mechanical testing to actually characterize that, but because we're using phase separation to get this, to get the core in the sheath, we can expect there's going to be some liquid crystal dissolved in the polyurethane, which might sacrifice the mechanical properties a little bit. But again, because polyurethane is such a mechanically robust material, we think that it wouldn't sacrifice its viability for application. Yes?
Do you think you could put this in a tape, like an adhesive tape?
Yes. What do you?
So kinesio,
Mm-hmm.
the athletes use it to basically stretch on the muscles while they're working out, and doctors put it on and they measure the tension, and if you had it based on color,
Yeah.
you could see like how far the tape was placed on there, they'd know how to prescribe treatment.
I think that's an excellent application for this, and I think it would fit right well into this technology's strengths. Great, thank you.